This is the, I think the 4th tutorial session, if I'm not wrong. And the idea here is going to be to look at some algorithms for winner determination problems that are NP hard. Okay. So can I just quickly get a sense of people who are not familiar with terms like kernelization or FPT? So not okay. So I should probably spend some time defining it as I go along. So you've not seen parameterized algorithms before. Would that be right? Okay. All right. Fine. So I guess we'll get to that in just a bit. Let's just begin by warming up with min-max approval. So you remember the setting, right? So we have something we saw in the previous lecture. We have approval ballots, yes, and what we want is committee whose maximum distance from any voter is as small as possible. Yeah. Okay. So we want to. So this is sort of the. Let me use D sub h to denote the Hamming distance between two sets, and let's think of, so every approval ballot can really be thought as a subset of candidates, right? So, so what we want is, yeah, so we want that V star. So so the V's are let's see. So the max. So let's fix a V star, which is a subset of candidates. Okay, you may also additionally want V star to be equal to K. So let's say you're looking for a committee of a fixed size. So that's K. So some people like to ask for committees of size at most K, but I think we'll just stick to committees of size exactly K. Right. So you want that committee that minimizes the maximum distance from any voter. So this max is over all the votes in the profile. Okay. So that's the MAV problem. And I'm proposing here one fairly straightforward algorithm, borderline, yeah. So it's interesting because it completely ignores most of the profiles. So what I'm proposing here is, let's pick an arbitrary voter and take his take his vote. That's a subset of candidates. If that subset has size exactly K, then I just return that as the committee. Okay, and if that subset has size more than K, then I'm just going to knock off some people arbitrarily, right? So let's say that the size, the number of people that this voter approves is K plus L, then I'm going to just remove L people randomly, not randomly but arbitrarily, and return the remaining K. And if the voter approves fewer than K candidates, then I'm going to randomly add whatever deficit is there, right? So if he approves K minus L people, then I'm going to randomly add, again arbitrarily add L people, and then return that as the committee. So that's what I mean when I say complete S to a set of size K arbitrarily. Okay. So I want to argue that this is actually not such a bad committee. Okay. Even though the algorithm only takes into account the opinion of just one voter, it's still not very far from what the optimal committee would do. So this is in some sense an approximation, a constant factor approximation algorithm. So what I want you to think about is, why is this committee going to be off by a factor of at most 3 from the best possible committee? And one thing that you might find useful is the triangle property for Hamming distances. So yes. The output is, okay, so what I do is I look at the vote of one voter, right? So just pick your favorite voter V. Okay, and so if the size of, so let C sub V be the set of candidates approved by the voter V, right? So if this is exactly equal to K, then just return CV. And if it is more than K or less than K, right? So then here I want to augment arbitrarily, and here I want to just reduce arbitrarily. So here I'm going to pick, so let's say this is L, right? So let's say this guy approves L candidates. So here I'm just going to pick K minus L people arbitrarily from the pool of people that this guy doesn't approve of, right? And just add it and return that. And here I'm just going to knock off L minus K and return that. Okay. Is the output clear? Good. Okay. So let's just do this very quickly. So this is true for in particular, this is true for Hamming distances over sets. So let's say we have 3 sets over a fixed universe, x, y, and z. So the Hamming distance between x and y is at most the sum of the Hamming distances between x and z and z and y for any third z. Would that be clear? Let's think about why. So I think the proof may be fairly obvious using a Venn diagram, but one clean way to do this is to also write down the characteristic vectors for these sets. So let's just think about so these are, just think of these as 0, 1 vectors over the universe, right? So for instance, if your universe was so if my set is ABC, then the characteristic vector is going to be 1, 1, 1, 0, 0, 0, 0, and so on, right? So it's just standard notation for denoting subsets. So the Hamming distance between x and y is going to be all positions where the characteristic vectors differ. Yes? Because it's the symmetric difference, right? So if they're both 0, then they don't disagree. That doesn't contribute to the symmetric difference. And if they're both 1s, then those elements lie in the intersection, so that also doesn't contribute to the symmetric difference. So it's only when you have a 0 here and a 1 here, or a 1 here and a 0 here, that you have a problem, and that contributes to the Hamming distance, right? So I would argue that anything that contributes here contributes either here or here. Is that clear? Yes. The MAV is minimization, yes. So I want to argue that it's not that the MAV score of S star is not too large. It's at most 3 times the optimal score. Yeah, of the algorithm. Yeah. If it was a maximization problem, I would want to say something like it's at least half of the optimal, or whatever, some factor of the optimal. Okay, so back to the Hamming distance triangle inequality. Is this kind of clear as to what's going on? So, okay, so any position that's different for x and y, right? So let's say this is a 1 here and a 0 here. The same position at z can be either a 1 or a 0. Cannot be both, right? I mean, no quantum bits, right? So it's either a 1 or a 0. So which means that either this term or this term is going to get a +1 from this position, right? So every position that contributes something to here also contributes something either here or here, right? So, but then the point is that you could have more points of differences between, so you could have positions where x and y agree, but z is different. So that's why the at most. Yeah. So this quantity could be strictly bigger. Okay. Yeah. But the burden of proof is only showing that everything that contributes here has a contribution on the right hand side as well. So keeping this in mind, just think about how you would show the 3 approximation. It's not very hard, but just okay, let me just recap the overall argument for the benefit of the recording as well as anyone who's not tuned in. So we're making 2 claims here. So first of all, we're using D to denote the optimal MAV score, right? And okay, we're arguing by contradiction. Could also do it directly, but that's okay. So let's say that there is a V prime for whom the distance from V prime to V star is more than 3D. Okay. So just to recap the notation, V is the voter that our algorithm picked and then extended to K. So V star is the output of the algorithm and W is the optimal. Okay, so W is some committee which may or may not be one of the input ballots, and V star also may or may not be. So is everyone familiar with the vertex cover problem? Yeah, okay, all right. So this is something that you can try to do. It's a cute exercise. Okay, so just to refresh your memory, vertex cover is the following problem on graphs. So you're given a simple undirected graph and you want a subset of vertices that hits every edge. Okay, so you want a subset of vertices of size at most k. So in the optimization problem is to minimize the size of this subset, but the decision version is that for a given budget k, is there a subset of vertices of size at most k such that every edge has at least one of its endpoints in this subset. Okay. Sure, yeah. You can look at the decision version of MAP, yes. Wherein you say that, okay, here is, yeah, here's a threshold that I'm willing to tolerate. So the distance is D. Give me a committee which is at most D away from every voter in the pool. Candidates as vertices. So introduce a candidate for every vertex and maybe try and see if you can introduce a voter for every edge and what would be the appropriate vote to introduce, and somehow you want to associate the vertex cover with the optimal committee. And minus k minus 1. Okay, so let's think about it. Okay, so again, let me just recap for the record. So our candidates are vertices and voters are edges, and the votes are pretty much indicator vectors, right? So they're ones. So they basically, okay, so essentially these are two-sized subsets in the natural way, right? Now the target Hamming distance is proposed to be n minus k minus 1. That should be roughly correct. I usually get these off by 1, off by 2, off by k errors, so we'll figure it out. But okay, let's try to do this in one direction. So suppose you do have a vertex cover, the natural thing is to pick that vertex cover as the committee, and if you do that, then what is the worst distance that you can have from any voter? Well, so let's take a prototypical edge between, say, U and V, right? So the committee is guaranteed to agree on one of these, right? Because the committee comes from a vertex cover. So on these two guys, you're going to have a disagreement of at most one, right? And then on the rest, even if you go all out and the committee looks like this, you're going to have an additional disagreement of at most another k minus 1, right? Would that be right? Sorry? Plus, okay, so everything else is zeros on both the committee and the vote, right? So this disagreement, so think of this as you have a committee of size k out here and you have this edge of size 2, right? So as far as the symmetric difference is concerned, you're getting 1 from here and k minus 1 from here, right? So in fact the Hamming distance appears to be, I mean, it seems like we can manage a Hamming distance of k, right? So let's modify the target Hamming distance to account for that. So probably n minus k minus 1 works if you do it the other way, where your sets are of size n minus 2. So you have zeros on the edges and ones everywhere else. Maybe that's when that works. So okay, essentially there are 3 possible pictures, right? Either your committee completely contains the edge UV, okay, or you have it jutting out like this, or it's completely disjoint, right? So in this case, the Hamming distance, as we discussed, is k. In this case, the Hamming distance is in fact k minus 2, right? Because that's the symmetric difference is essentially the committee minus the edge, so that's k minus 2. And in this case, the Hamming distance is k plus 2, right? Because the sets are completely disjoint. So this is the situation that you want to avoid. This is a situation that you cannot guarantee that you will get into, right? Because it's not clear that you can always cover both endpoints of every edge. So this is the right threshold, right? The threshold is k plus 1, oh sorry, just k. So that seems like the sweet spot. So let's now argue, so the forward direction should be clear. In the reverse, let's say that you have a committee that does achieve a Hamming distance of size k from every voter. Claim is that the vertices corresponding to the candidates in this committee actually form a vertex cover, which is again clear for the same reasons. If it didn't, then you would have this situation, and this situation leads you to a Hamming distance that's off limits. Yeah. Because if it wasn't a vertex cover, that means that there is some edge that's not covered by the committee, but then let's go to the vote corresponding to that edge, and the Hamming distance between that vote and this committee is more than k. Yes? You convinced? So here the forward and reverse directions are really very, very symmetric. The arguments are very similar. Okay, fine. Okay. I don't know if we have time to get into the d to the 2d branching algorithm for closest strings. So let me do a simpler one, and maybe this can just be an actual homework problem. So I'll put up the problem set on the website, and maybe you can even remember the question. But let's just go to a slightly different problem, but it still has this flavor of distances and so forth. I was tempted to throw this in because we've looked at swap distances quite a bit in the context of single crossing profiles. And although this isn't about restricted domains, we're just going to encounter this notion of swap distance again. So I think we have already defined the Kemeny, the notion of a Kemeny score and the notion of a Kemeny consensus, but let's just go over it again. So we are back to the setting where your inputs are rankings, and we just define the swap distance again. So given 2 rankings, the swap distance between them is the number of pairs of candidates over which these guys disagree. Okay, so that's what is up there. Now, given a ranking, the score of that ranking with respect to an entire profile is the sum of its swap distances from each of the guys in this profile. Okay, so we're back to this notion of distances, but now instead of saying that I'll only look at the worst distance, I'm looking at the sum of the distances. Okay. And since we are dealing not with approval ballots but rankings, our notion of distance has changed a little bit. It's not Hamming distance, but it's the swap distance. Okay, so also computing the ranking that has the smallest possible Kemeny score turns out to be NP hard, which is in slight contrast with the approval ballot setting, because okay, I don't have a slide for it, but in the context of approval ballots, if you think of the sum question, right, if you think of the min sum voting rule, then it should be fairly clear that that is easy to compute. It's easy to compute the optimal committee under min sum. So if you want the committee that minimizes the sum of the Hamming distances to each of the voters, then how do you do that? So you want, instead of minimizing the maximum Hamming distance, I want to minimize the sum of the Hamming distances. So that would be the min sum voting rule. So how do you come up with the optimal committee? So you could ask for a size k committee or just an optimal committee of any size. Both of these should be easy. Yeah, greedy based on what? The candidate who's approved the maximum number of times. So does that sort of work? Yeah. Okay, just think about it. That actually would work in this setting, because everyone who doesn't approve a candidate is going to contribute 1 to the score anyway. So even on a per candidate basis, you might as well. So essentially, just fix any candidate and look at the number of disapprovals that they have, right? So that is kind of a lower bound on on the min sum quantity. You're going to so if you pick this candidate, you're going to get that sort of a score anyway. So that's if you think about that just a little bit more, you should be able to argue the optimality of greedy. Okay, so picking the candidates who have, so rank the candidates in terms of number of approvals and pick the top k. That should work. Okay. Right. Here, unfortunately, there's no obvious. Well, okay, I don't know how to put it, but basically, this is a fairly severely NP hard problem, in the sense that I think it's NP hard even when the number of voters is a constant, like a small constant, like 4 or something. I think one of you presented this result last summer. Yeah, how many voters do you remember? 4? Okay, all right, so fine. So it's pretty hard to compute the Kemeny optimal ranking, but let's just see what's the next best thing we can do. So there are 2 or 3 notions of the next best thing that you can do when you encounter an NP hard problem. One is what we've already seen, which is to, in polynomial time, try and compute a solution that's not very far from optimal. So that's settling for an approximate solution. Another thing that you can do is look for algorithms that are expensive time-wise, but then try to optimize that expense as well. So for instance, an obvious algorithm for computing the Kemeny optimal ranking would be to just go over all possible rankings, and that would be m factorial. And let's say that you have some way in which you can improve that to 2 to the m. That would already be a significant improvement, and so on and so forth, right? So here I'm asking you if you can come up with an algorithm that finds the Kemeny optimal ranking in time 2 to the k, where k is the optimal Kemeny score. Or in other words, let's just fix the decision version of the problem, where I'm asking you, can you come up with a ranking whose Kemeny score is at most k? Okay, and okay, so depending on the situation, this may or may not be a great algorithm. How bad can k be? What is the worst? So what's the worst possible value that the Kemeny score can be for an instance? N squared. Okay, so there are n votes, and you're summing up all the individual scores, all the individual swap distances. So it's n times, not sure that it's n, because the swap distance can be as bad as m squared. So it can be n times m squared, right? But of course, in most settings, it's probably reasonable to say that m squared may even be less than n. So your bound is probably worse than mine. But in any case, yeah. So n times m squared. So k in general can be pretty large. But let's say we're looking at instances where the rankings are not very different from each other somehow. Let's like in a restricted domain setting, for instance, that would be true. In which case the value of k may not be all that bad. In which case it would make sense to look for an algorithm like this. So in particular, if the values of k are like logarithmic in n and m, then this is practically a polynomial time algorithm. That's the other end of the spectrum. So there are situations where this sort of a running time would even be useful. But just independently of the utility of this, let's just think about how we would come up with an algorithm like this. So let me maybe just give you some starting points. So what can we say about pairs of candidates that, so let me say that a pair of candidates forms a conflict pair if there's at least two voters who disagree on these candidates. Okay, so you have A and B, and there's somebody who likes A more than B, and there's somebody who likes B more than A. That's a conflict pair. What can you say about a candidate who doesn't participate in any conflict pairs? What does that mean? Okay, so candidates who are topmost, so if there is a candidate that's ranked at the top for everyone or at the bottom for everyone, they certainly don't participate in any conflict pairs. But there are also more situations where
So basically there's a subset of candidates who are always above him.
Right, exactly. So there is a subset of candidates who are always ranked above this guy, and there's a subset, the rest of them are always ranked below him. That's when somebody, so their position is essentially fixed, right? And it should be easy for you guys to see that any optimal Kemeny consensus ranking also places him at the same position. There is no point in placing him anywhere else, right? So if there's a candidate C that doesn't participate in any conflict pairs, it means that C occurs at the same position of every candidate, okay? And therefore you can actually knock this guy off from your input because you know where you want to place him at the end, so you don't have to worry about him, right? Okay, so now let's consider any pair of candidates after we have cleaned up these guys who don't participate in any conflict pairs, right? So let's pick an arbitrary pair of candidates. We know that, or let's pick a candidate. We know that they participate in at least one conflict pair. So let's pick such a pair, AB. So what I'm going to do is I'm going to branch on the two possibilities that the final optimal ranking places A above B versus the final optimal ranking places B above A, because these are the two possibilities, right? And then I basically make this local commitment, and now I have a new instance of which is essentially the same profile, and I'm saying, okay, now give me a consensus ranking that respects some pairwise orderings that I have already prefixed, okay? And now my target Kemeny score, and this is the key thing, what is the target Kemeny score that I'm looking for? Yeah, so it's k minus 1. So it's reduced by 1 because I know that, so because AB is a conflict pair, in both of these parallel universes that I get into, I have already incurred a cost of 1 in the Kemeny score, right? So what I know is that, okay, so what I know is that opt, whatever opt is, whatever the optimal ranking is, either does this or that, okay? So I'm going to explore both possibilities. In this sense, I'm being exhaustive. But if opt does this, then I've already made one voter, at least one voter unhappy, right? Because AB is a conflict pair, so there is somebody who prefers things the other way. And here there is also somebody who prefers things the other way. So in both cases, I'm looking for a Kemeny ranking which is consistent with this, but where now k has dropped by 1, okay? And essentially I recurse and keep repeating this process until I've either had enough pairs to determine a ranking completely and I can stop, or when k goes down to 0, because what does it mean that k is down to 0? right? You cannot afford to have any more conflict pairs, right? Because now I'm saying, give me a ranking that's consistent with these pairs and whose K-mini score from the preference profile is 0, right? And that would mean to say that the profile must be full of identical votes when projected on these remaining candidates, okay, whose fate is yet undecided. Okay. Yes. No, we're not left necessarily with K conflict pairs because, okay. Yes, so in fact I was just going to come to that next, which is to say that you can in fact deduce that you have a no instance of K-mini score if you have too many conflict pairs, right? Because, so let's say in particular that you have more than K disjoint conflict pairs, right? You will never be able to satisfy, you'll never be able to come up with a ranking that has a K-mini score of K in this case, right? Yeah, so, and if you modify, yeah, and you can argue that a little more precisely to say that the number of conflict pairs is in fact bounded by 2K, yes. So, yeah, cool. Okay, so this is essentially a branching algorithm that has, if you're familiar with how recursion works, this is depth K, and that's why this is 2 to the K. And as I said, if it seems too good to be true, you can reset your intuition by realizing that K is typically a very large number. Okay, it's just that, so because the total amount of potential conflicts that you can have, or the K-mini score of an instance can be really, really large. Okay, so it isn't anything fancy that we're doing here. To address this issue of can we do better, you need to think about if you can analyze this algorithm better or come up with better branching strategies, right? So here we're just branching over one conflict pair. Also, okay, so in the worst case, it's going to be K minus 1 on one of the branches, but in a typical case, you're actually going to make a lot of people unhappy when you do it, when you make one of these commitments. Because essentially the entire pool of voters is split into two parts, one that prefers A over B and one that prefers B over A. And when you commit to A over B, you're going to make the second part completely unhappy and the other way around. So these drops are in practice going to be actually much larger, okay? So, but I don't know how to formalize that, but coming up with better branching strategies is something that certainly works. So, okay, and by just analyzing the structure of conflict pairs carefully, and also realizing that you cannot have too many duplicate votes. Okay, so think about what happens if you have one preference ranking that's replicated more than K times, right? So let's say more than K voters share the same ranking, then what can you say? Right, so either the consensus, so this better be a ranking that has a total consensus score of at most K, or you can in fact say no, you can say that there is no ranking which has a K-mini score of at most K. Why is that? Because if it's not going to be this ranking, it's going to be some other ranking, and that ranking is going to displease all of these guys by at least one each, and you've already overshot your budget, okay? So in this case, when you have more than K people that share a common ranking, you already have your answer, which means that in any non-trivial or interesting instance, any vote can be replicated at most K times. So combining this along with what we have discussed about K-mini pairs, you can actually argue that any given instance can be cleaned up to an equivalent one that doesn't have too many voters or too many candidates in terms of K. So I'll let you think about that as like a fun food for thought type question. And I'll try to supplement the question that we omitted with some hints, put it in a problem sheet and give it to you to think about. So in the interest of time, I think let's close this tutorial here and maybe take a 2-minute break to just set up the slides, and we'll continue with the last lecture of the day.
Tired, right? It's getting late in the day. So this is a very interesting topic, committee selection with ranked ballots, right? So we spent a lot of time talking about committee selection with approval ballots. Arguably, ranked ballots are at least as interesting, possibly more interesting. Certainly, if you look at the volume of research on committee selection with ranked ballots, it's much larger. But given that we don't have much time and it's the end of the day, so I won't go into detail into this fascinating area of research, But what I want to do, I want to show you a few voting rules, including my favorite rule in this domain, Chamberlain Current rule, and I want to connect this to our kind of discussion of restricted domains and show you an algorithm for that rule for single peak preferences. Okay. So the basic model, so again I'm borrowing slides from Piotr Folishevsky, is we have inputs that are ranked ballots, so voters order candidates, and we want to output a non-empty family of size k committees. So here's the simplest thing you can do. So suppose you have a scoring rule, for instance border rule. Well, you can compute the border scores of all candidates and kind of pick the candidates with the highest scores. So for instance here, okay, so let's look at the selection. So what is the border score of the red guy? He gets 4 points from the first voter, 2 from second and third, 1 from fourth, 2 from fifth, 4 from sixth, so that's altogether 15. So we compute the border scores of all voters. So, right, so these are the numbers. So, and if our committee size is 2, then it should be red guy and green lady that we select. Right, so that's a very simple rule, also very efficient, very easy to compute. So this is one example of things you can do. So border, if you think about kind of justified representation type of criteria, border rule is not going to do very well in regards to that. Right? So border rule sort of focuses on candidates that don't necessarily cover everyone, but are sort of ranked highly in at least some of the votes. So it's kind of a rule of that flavor. Okay, so single transferable vote is another interesting rule that we know from single winner setting, and that actually can be adapted to multi-winner elections. So the way that works is slightly different from single winner elections. So remember, how did single transferable vote work in single winner elections? So we were looking for a candidate with majority support. Now, if that existed, we selected that guy and we were done. And if that didn't exist, so we started deleting candidates one by one. So basically, the way single transferable vote operated is we eliminated candidate until we had one candidate with the majority, and then we were done. Now our goal is to select a committee. Now to add someone to a committee, we don't have that guy to have majority support. So we just want him to have a reasonable support. So reasonable, again, we can define it as kind of in the previous session by n over k. So what is slightly more traditional is to have a, well, slightly larger number is n over k plus 1 plus 1. N divided by k plus 1 plus 1. Right, so that's roughly n over k, but there are technical reasons to prefer this larger number, so I don't want to go into that now, but I'm happy to discuss that tomorrow in person. But the intuition is the same, right? So a group of size roughly n over k deserves representative. Okay, so now let's look at our profile. So if we have so this is sort of our notion of large group now. So if we have a candidate ranked first by members of the large group, so we want to select that candidate and add him to the committee. Okay, so now what do we do? But we are not done yet, right? So we want to select an entire committee, and we just selected one candidate. So now one question we may want to ask is, what do we do with the voters who approve him? Right? They're already satisfied. They're already represented in the committee. So perhaps we should delete them. Well, that seems slightly unfair if there is a lot of them. Right? So again, from kind of EGR type of argument, if you have like 5 times n over k voters who will approve that guy, deleting all of them at that point seems unfair. So what STV does is selects that many voters among those who rank our first guy quota times and deletes them. So this selection can be random, so it can be arbitrary based on some procedures, but the point is that this many voters are deleted, and then we proceed. Okay, so what happens, so in the next step we try to do the same thing. So now what happens if we don't actually have a candidate ranked first by this many voters? Then we do what we do in the case of single winner voting. Right, so we find someone with the smallest number of first place votes and kick that guy out. Right, and that increases kind of their plurality scores, the number of times someone is ranked in the first position for other candidates. So hopefully then we have some candidate who meets the quota. Right, so if you select that candidate, delete quota number of candidate voters and proceed. Okay, so let me illustrate that again on these elections. So suppose again we want to select a committee of size k. So the quota in that case will be 3. Right, so this calculation for the case of n equals 6, k equals 2 boils down to the same as n over k. Okay, so now, so we are looking for someone who is approved by, who is ranked first by 3 voters. Do we have anyone here? Sorry, no. Okay, so now we want to delete. So now we want to delete someone. We want to delete someone with the smallest number of first place votes. Who is that? That's a trick question of sorts. There's someone with 0 first place votes. That's the green candidate, right? Green lady. So we delete green lady. Of course, this is not going to have any impact because that's not going to transfer any votes to anyone. But technically, we first have to delete her. Okay, now this is done. So now we have, okay, so next, still we don't have anyone with 3 votes. So now we have 2 candidates for deletion, blue guy and orange guy. So we delete one of them. Again, there's an issue of breaking ties. Okay, we delete the orange guy. So an extra vote goes to the red guy. And now the red guy has 3 votes. So we can add him to the committee. Wonderful. So we add him to the committee. So this is sort of the uninteresting case because we have exactly 3 people ranking him first. So we delete all of them. If there was 4, we would have to decide which one of these guys to leave in. But since there are exactly 3, we are just deleting all of them. Okay? So we can now also delete the red candidate from the remaining votes. Okay, so now we still have 1 candidate to select. So the quota is still 3. Right? So no one has 3 votes. So we delete the candidate with the smallest number of votes. So that's the blue guy. So we delete him. Right? And now the pink lady is selected in the committee. So put the pink lady is here. Okay, wonderful. Okay, so one reason actually why in STB we have this quota is that if we run this procedure with n over k, we may end up deleting all voters before we have actually selected k committee members. Right, and if we set quota like that, so it's a nice exercise to prove that this is not going to happen. That if we run this procedure in this fashion, we'll actually have a committee of size k. So STB actually does well kind of in multi-winner setting on a variety of criteria, kind of JR style criteria and also other criteria. As in single winner setting, it's not monotone, so that's a downside. But apart from that, it's actually a very nice rule. Okay, so it's also hard to compute, so that's also inevitable. But it's also a rule used in practice. So when I mentioned about STB used in Australia, right, I actually sort of cheated you, right? Because I was talking about STB as a single winner rule, and the way it's used in Australia and New Zealand is used as a multi-winner rule. So it's used in this fashion, right? So each kind of electoral district there produces several members of parliament, right? And they are elected from the nominated candidates using multiple winner STB. And okay, and this is how STB works. So I'm not going to say much more about it. So now I want to switch to the rule called Chamberlain Current. Okay, so this is sometimes happens. So PowerPoint screwed up my spacing. Let me see if I can fix it quickly because this is just not pleasant to look at. Okay, what the hell? If I change fonts. Committees, and then I'm going to say we select the committee with the highest score. So let me now explain how voters score a specific committee, namely committee BD. So they're going to score it using border scoring function, but this is going to be different from k-border. Okay, so here's what my voters are going to do. So voter 1 looks at the committee BD, so it's BD that we're trying to score, and he looks at his favorite candidate in BD. His favorite candidate in BD is B. So the border score that he assigns to B is 3. Right, so he says, okay, I evaluate committee BD according to my favorite person in that committee, and the score of my favorite person in that committee is 3. Okay, so the second guy does the same. So he looks at committee BD, he says, okay, my favorite guy in BD is B, I rank him in top position is worth 4, so I give that committee a score of 4. Right, so in a way, so voters evaluate the committee optimistically, according to the most favorite person, and they look at the border score of the most favorite person. Okay, so so now we've got these numbers. This is how each voter evaluates this committee. So with these numbers, there are 2 things we can do, right? So one will be Maximin style, and the other one will be kind of the style of all other voting rules we considered, right? And one I'm going to call egalitarian and the other utilitarian. Egalitarian score of a committee is the minimum of these numbers, right? So look at this 4th guy. He really doesn't like the DB committee much, right? So his utility from that committee is just 2. And therefore, maybe DB is not a great committee. It doesn't really help that guy. right? Or we can look at the utilitarian Chamberlain Current score and add up these numbers, right? So these are two options. So this is how voters evaluate individual committees, and the goal is to select the committee with the maximum score. Committee of fixed size k that maximizes that score. Okay, so if you want all that, not in a picture, but in a formal expression, so let's do that. So the score that the voter has for a candidate, this is the border score. Score that voter assigns to a candidate is S if the voter ranks that candidate in position C minus S. These are our regular border scores. That's how we always define them. And now the score that the candidate has for a committee is the maximum score for committee members, right? The number you assign to the highest candidate. Right, and then, okay, so utilitarian outputs a committee that maximizes the sum of scores, and egalitarian outputs a committee that maximizes the minimum score. So you can also call egalitarian a maximin type of Chamberlain Current. Okay, so you can ask me again why I'm using border scores for that. I don't have to. So one thing I can do, for instance, I can use approval scores here. Okay, so let me ask you what happens if the scoring vector I used here was not 4, 3, 2, 1, 0, but 1, 0, 0, 0, 0. What sort of rule would that give me? So hint, this is a rule you have seen today. It's sort of greedy coverage rule of sorts. Right, so basically you are saying, okay, so a voter is going to be happy with the committee only if this committee contains the top candidate of that voter. Right, so each voter ranks a committee 0, 1, sort of approve, disapprove. And it approves a committee only if the committee contains his top guy. Right, so we are basically trying to, so we are trying to select a committee that maximizes the sum, that kind of covers as many voters as possible. Right, so this is our 1, 0, 0, 0 approval vote rule, except, so if we are to treat these votes as approval votes for the top candidate, as plurality votes, so that would be kind of our approval vote. So you can also do it, instead of doing it for 1, 0, 0, 0, you can do it for the case when you have a bunch of ones and then zeros. Right, so in fact you can allow an individual score vector for each voter. Right, and that has the effect of allowing each voter approving some number of candidates. Right, and that sort of brings this down to the approval ballot setting. Right, so if you allow those scores to be individualized and consist of ones and zeros, right, that exactly brings us down to approval ballot setting. But okay, so border is sort of natural, so it's natural in the single winner setting, it's natural in this setting. Okay. So now we have a formal definition. So Chamberlain Current rule is wonderful for a variety of reasons, but it's NP hard to compute. So it's sort of easy to see that it's hard to compute if you look at the approval-based version, because then it becomes maximum coverage. Right? So if you look at the approval score where you approve not just one candidate but many, right? So then it becomes kind of a standard maximum cover problem. Right, and with border scores, it's also actually NP hard. It's slightly more difficult to show, and I'm not going to show you the hardness proof, but it can be proven to be NP hard, which is sort of, well, okay, not entirely surprising. So let me talk a little bit more about the comparison between this 1-0-0 approval voting and Chamberlain Current, just to illustrate. And let me, okay, so I'm now going back to Peter's slides. Okay, so 1-0-0-0 approval voting, so basically says, okay, so for each, so this is the rule, this is the maximum coverage rule. So we evaluate the committee according to how many voters it covers. Okay, so let's try to evaluate the committee that is orange and purple, right? So this is very cleverly drawn by Piotr to combine orange and purple, right? So orange and purple covers these three voters, right? Okay, so we are now looking at approval ballots, right? So this ballot includes the orange guy, these two ballots include both orange and purple, so these voters are satisfied, right? So the 1-0-0 AV score of this voting rule is 3, right? So that satisfaction, happiness is 3. If we now look at red-green, then that satisfies only 2 voters, so the happiness there is 2. And if we look at red-orange, the happiness is 4, right? And this is obviously the best one to choose, right? So this is what you do if you have approval ballots. So what you do with Chamberlain Current is in a way very similar. So now we are in Chamberlain Current setting. So now instead of approval ballots, they have proper ranked ballots. So we are still trying to cover voters, but covering voters means a different thing when they have ranked ballots. Right? So covering a voter's approval preferences is easy. Right? So it's easier to understand what it means. You want to have one of his approved candidates in the winning set. So what does it mean to cover a candidate who has a ranked ballot? It means to select. So we cannot just cover them. It's not binary. We try to cover him as highly as possible, right? So we want to move as highly up as we can in his preference ranking. So again, if we choose now orange and purple, okay, so the colors are not displaying properly, right? So there's a purple rectangle here which you cannot really see, right? Or maybe you can. So there's very weak shade of that purple rectangle, right? So if we pick orange and purple, so we cover this candidate fully, we cover this voter fully, we cover this voter up to this point, this voter up to this point, and these voters fully, right? So our sort of coverage frontier goes like that, right? And that gives us the Chamberlain Current score. If we choose red-green, okay, so that displays better, right? Okay, so this is our coverage frontier, right? So, and the score is this. Right, so again, we are trying to cover voters by pushing this coverage frontier as much to the left as we can, right? Or in other words, we are sort of interested in the area of this in this colored area, right? So now if we can finally do a red, purple, and that kind of covers all these voters almost completely, and these voters completely, so it's better, right? So that's sort of the same intuition that's kind of transplanting the idea of maximal coverage to ranked ballots. So that's one reason why Chamberlain Current is a very natural appealing rule. Okay, so it's hard to compute, but well, we have our kind of ideology of focusing on restricted domains when we have a hard problem. Kind of not approximation algorithms, not parameterized complexity, well, restricted domains, right? So this is kind of what I like to do. And Chamberlain Current is actually turns out to be easy to compute, polynomial time computable for single peak preferences. And this is so this I think is an illustration of a very nice phenomenon that I didn't get a chance to talk about yesterday because I didn't have an illustrative example, but I have now. So let me show you how the algorithm works, and then I'll try to argue this is an example of a very nice algorithmic paradigm. Okay, so what we want to do now is we want to compute a winning committee under Chamberlain Current for single peak preferences. Note that I'm not trying to output all possible winners, right? So there can be many committees with the maximum Chamberlain Current score, even with single peak preferences. I'm not making it my job to find all of them. For one thing, there can be exponentially many, right? So I don't care. I just want to output some winner, right? So this is like STV with lexicographic intermediate tie breaking. I want one STV winner, and here I want one winning committee under Chamberlain Current. So I can talk briefly maybe at some point what happens if you want all of them, so it's not very hard, but for now I just want one. And the theorem, so this is Betzler, Slink, Ullmann, 2013, so fairly recent. So both for egalitarian and utilitarian version Chamberlain Current, so we can compute a winning committee. So as a warm-up, let me start with the egalitarian version. Okay, so let's think about it. So what does it mean that we want to maximize the egalitarian Chamberlain Current score? So what can be the egalitarian Chamberlain Current score? Right? So we measure it by satisfaction of a voter from the committee. Right? So it's a number between 0 and m-1. Right? So these are the values it can get. Right? So we can go over all these values, and for each of them, we can check if there is a committee that provides this egalitarian Chamberlain Current welfare. Right? And then we can pick the best value. Okay, so now suppose I have fixed. Okay, so suppose I fix S score. So I'm going downwards from the maximum one, from making everyone maximally happy to making everyone, at least somewhat happy. Right? So, and I want to select if the committee of size K with egalitarian score at least S. So one that provides everyone satisfaction of at least S. Okay, so it's not immediately clear to me if I'm finishing at 1 rather than 0 here. I hope it's correct. If not, then maybe it's 0. Okay, but okay, so suppose now I have S. So let me look at a voter. Right? So I have my single peak preferences, so I don't have a picture here, but by now you can imagine it well enough. Okay, so what are their committees? Okay, so for each voter, who who are the candidates who have score S or higher, right? So these are the candidates positioned that appear in top M minus S plus or minus 1 positions, right? So this is a prefix of that voter's preference. So that's a contiguous segment in our single-peaked universe, right? So for voter 1, so these are the guys who would give him satisfaction of S or higher, right? So for another guy, for voter 2, these are the candidates who would give him a satisfaction of S or higher, right? So he doesn't need to have all of them in the committee. It's enough for him to have one, right? So these are the good candidates for voter 1, and if he has one of them in the committee, then his welfare is at least S. So for voter 2, it's a different segment. For voter 3, it's a different segment. For voter 4, it's a different segment. Okay, so now we can select K candidates. What does it mean geometrically? Stabbing, right? So we want to stab all these intervals with K points, right? And that's an easy problem, right? So it's sort of standard kind of computational geometry in 1D algorithm. Can we pick K points to stab all n intervals, right? So that's kind of standard dynamic programming exercise, so that's easy. Okay, so that was egalitarian. Okay, so utilitarian takes a little bit more work. So utilitarian is based on dynamic programming. So let me present this dynamic program to you. Okay, so as a first step, so let me try to reason in terms of marginal contributions again. So let me look at candidate. Okay, so imagine, so these are my candidates on the axis. Imagine I have a committee that is contained somewhere here to the left of Cy and contains Cy. Right, so maybe it's not size K yet. I'm building my committee gradually. Maybe it's some smallish set of candidates. All I know about it, it's to the left of Cy, and it specifically contains Cy. Right, and now I'm exploring the possibility of adding CZ to it. What's going to happen if I do that? Well, let me see what kind of impact this is going to have on the happiness of my voters. Okay, so voters come in 2 flavors, basically. So I have voters whose top choice sits to the left of Cy. What is the impact of adding CZ to the committee on those voters? Nothing, right? Because I say explicitly that Cy is in the committee, not just to the left of Cy, but including Cy. And since my guy's top choice is here, he prefers Cy to CZ, right? And because he only cares about his top choice in the committee, CZ does nothing for him, right? So for those voters, the impact is 0. Well, I also have voters whose top is to the right of Cy. So it can be between Cy, CZ, or it can be over there. I don't care. So in both of these cases, here's what I can say. Okay, so let me maybe focus on this case first. So I have a voter whose top is here. So what can we say about the identities of his most preferred committee members? Whom does he like best in the committee? Okay, so we don't know for sure, but we can cut it down to 2 possibilities, either CZ or Cy. Right, so the rest of the committee is sitting there somewhere, right? So for our voter, for this guy, they're beyond Cy, so he prefers Cy to all of them. We don't know if he prefers Cy to CZ or vice versa, but certainly he prefers Cy to all other guys except maybe CZ. Right, and for the guy who sits there, okay, so he definitely prefers CZ to Cy. Right, so basically for all other voters, how much happier they're going to be when we add CZ, we can measure that just by comparing their satisfaction from Cy and CZ. We don't have to look at the rest of the committee, right? And this is exactly the sort of feature we need for dynamic programming, right? So for dynamic programming, we need this sort of clean boundary separation, right? So this guy doesn't care what happens to the left of this point. All he needs to know about this committee that it contains Cy. Okay, so what we can say now is that V's gain from adding CZ to the committee is a maximum of, okay, so either he likes Z more than Y, and then he adds the difference, kind of then adding C contributes the difference between the scores of those 2, or he actually prefers Y to Z, in which case this difference negative, right? And then, okay, so he doesn't actually lose anything, so it's maximum of Z and his possible gain. Okay, so we can write it like that. Okay, so yeah, so the point I was making, to compute this marginal contribution, we only need to know Cy and CZ. Right, okay, so this is the gain of voter V, and obviously we can sum this quantity over all voters. Right, so that would be the marginal contribution of CZ to the committee. Okay, and these are the ingredients we need for the dynamic program. Okay, so how is the dynamic program going to work? Well, we ask what is the maximum score of a committee that is first of size S, and second is contained in the prefix up to Z and contains the last point of that prefix. Right, and then, okay, so once we have computed all of these things, so the optimal committee would be the one where S equals K and Z can be anything, right? So we don't know in which prefix the optimal committee is actually contained, so we have to check all possibilities, right? So we go over all possible Z's and substitute K for S. Okay, so once we have computed that for all S and Z, we know what is the score of the optimum committee. Okay, so this is computing the score, but like always in dynamic programming, if you can compute the score of the optimal committee, you can sort of use that to actually find the optimal committee. So for now, I'm focusing on the score. Okay, so now how do I compute these things MSZ? Right, and okay, so I compute them inductively, building up from Z equals 1 to Z equals M. That's kind of standard dynamic programming fashion. Okay, so what is S? Well, S goes from size 1 to, okay, so I'm only interested in committees of size up to K, and of course, if I'm computing for a fixed Z, it can't be bigger than Z. Right, so this is the range of S I'm computing it for. Okay, so now how do I do it? So let me fix Z, so Z is somewhere there in the middle. So I'm asking what is the best committee of size S that is contained in this prefix and contains CZ. So to do that inductively, I have to guess who is the previous committee member. So I know that CZ is the last, so I have to guess who is the second last. Right, and the second last can be anyone here. So I have to go over all possibilities. Right, so let's say that the second last guy is CY. Okay, so then the score of my optimal committee is the optimal committee of size S minus 1 contained in this prefix and containing CY plus the marginal contribution of CZ to CY, right, which is what we computed in the previous slide. So the formula is this. So I pick the best Y, and for every fixed Y, what I'm computing is the best committee sitting in the prefix of up to CY and containing Y, and the marginal contribution of CZ to any such committee. Right, so that's exactly what I need to look at. Okay, and well, okay, so I believe I argued correctness, so you can see that it's efficiently computable kind of from the way it develops, right? So it's sort of, well, quadratic, something like that. So S, the range of S is up to Z, Z is up to M, the range of Z, okay, so it's quadratic in the number of candidates, right? And the actual, in the computation here, right, so this computation is linear in the number of voters. So we are looking at M squared then, right? So, which is pretty reasonable for a dynamic program, right? And this way we can compute optimal Chamberlain Current committees for utilitarian Chamberlain Current. Okay, so what's interesting about that? So the interesting thing is this general phenomenon. Social choice theorists came up with single peaked and later single crossing preferences because they gave them Condorcet-Winners, right? Now or transitive majority preferences. Now Condorcet-Winners are not relevant here, right? So in case of committee selection, or in case of at least Chamberlain Current voting rule, we don't care about Condorcet-Winners at all. We want the best committee. So the way we use the axis is not to give us the Condorcet-Winner, but to give us a basis for the dynamic program, to give us an ordering of things we can work with, right? And a lot of algorithms developed in recent years kind of to do things, to compute things for single peak, single crossing preferences, kind of use this paradigm. So they're based on dynamic programming that uses the ordering of voters or ordering of candidates as the basis for the dynamic program, right? So these equilibrium computation algorithms and a few other applications are used for these purposes, right? And this is completely foreign to social choice theorists, right? Because, I mean, dynamic programming is normally not how they think about collective decision making. So the beauty of that is that these dynamic programs, okay, so the notion of Condorcet-Winner is very fragile, right? So if your preferences are not single peaked on a tree because of a small change, okay, you no longer have Condorcet-Winners, right? So things break apart, right? If your preferences, on the other hand, if your preferences are not quite single peaked on a line, but maybe, say, single peaked on a tree that is almost a line, then dynamic programs are typically robust to handle that. So one example would be if your preferences are, instead of being single peaked on a line, are single peaked on a circle, you can define that notion in a similar manner, right? So you can make your dynamic program to work on circles, right? But on the other hand, for Condorcet-Winners, it completely ruins things, Right, so that's a completely different use of single-peaked, single-crossing preferences from what Arrow envisioned in his original paper, Arrow and Black in the 50s. Right, so, but as computer scientists, this is something that we came up with and we should appreciate. I believe this is the first example of this use of dynamic programming on single-peaked, single-crossing preferences, but I may be wrong, I'm not 100% sure. Okay, so anyway, so that was single-peaked preferences. So actually for single-crossing preferences, again, there is a dynamic programming algorithm. And so again, for utilitarian Chamberlain Current, so we can compute an optimal committee. Okay, so let me backtrack a bit. Okay, so now I'm talking about utilitarian Chamberlain Current and single-crossing preferences. And again, I want to compute an optimal committee. And the claim is that there exists, again, a polynomial time algorithm. So let me first state a lemma, and it will be very similar to the lemma we proved in the tutorial, and then let me state the theorem. Okay, so here's a lemma. So the lemma is about the structure of an optimal committee. So I claim that the optimal committee behaves like this. So I have my list of voters, so this is the single crossing order. So I'm going to break it into blocks. Right? So now the first block is going to be represented in the committee by candidate A, in the sense that among the committee members, the favorite candidate will be A. The second block will be represented by B, and etc. The last block will be represented by Z. So in terms of whom the voters prefer kind of in the committee, they come in blocks. Right? So we won't, right? So when we look at the committee, all the guys who prefer a particular member of a committee appear contiguously in our block, in our sequence of voters. And moreover, so we can see something about this order of preferred committee members. Right, so these guys prefer A among all the committee members, these guys prefer B among all the committee members, those guys prefer Z. So we can actually say something about the order of A, B, and Z in the preference of the first voter. Right, and this order is voter 1 prefers A to B, etc. to Z. Right, so in a way, right, so this is what we discussed in the context of single-peaked, single-crossing preferences. You can read things off the order of the first voter. Right, and this time it's the order of representative candidates in the committee. Right, and that lemma, I'm not going to prove it, but that lemma is the basis for the dynamic programming algorithm. Right, so with this structural result in mind, it's pretty easy to set up dynamic program and compute an optimal committee. Okay, so again, dynamic programming using the order of voters this time. Okay, so let me talk briefly about Chamberlain Current for preference as a single-peaked on trees. Okay, so this is sort of, okay, so I've been involved kind of in the single crossing paper, and single peaked on trees is really my stuff, so I like it. So it's my stuff with some students. Okay, so let me talk about egalitarian Chamberlain Current first. So now we have preferences single peaked on trees. So remember, egalitarian Chamberlain Current for preference single peaked on a line was interval stepping. Right, so now, okay, so now again we're in a similar situation. We are trying to, so for each voter, we are trying to provide him with one of his top S choices. So now his top S choices don't form an interval, but they form a subtree, a contiguous subtree. So now we are in a subtree stepping setting, right? So each voter has a subtree that he needs to have stepped, right? And we want to step all of them, right? And subtree stepping is also efficiently solvable, right? So this is also known in the literature, but again, so it's not that hard to do it greatly yourself. Now for utilitarian Chamberlain Current, things are harder. So remember, preferences single peaked on a tree include preference single peaked on a star. And preference single peaked on a star are MS. Okay, so you can take, okay, so let me take that back. It's not, okay, so what I said is correct, but for Chamberlain Current, actually stars work nicely. Okay, so anyway, so for Chamberlain Current, we don't have an algorithm that works for all trees, but we have algorithms that work for nice trees. So in the following sense, we have an algorithm that runs in X, that is in XP with respect to the number of leaves. So if you have a tree that has a small number of leaves, so like your tree is almost a path, but maybe it branches a little bit at one end and branches a little bit at another end, right? Then you can actually compute it in a Chamberlain Current winners in a reasonable number of times. So better yet, if your tree has a small number of internal vertices, so in particular if your tree is a star, this is why I was taking my words back. So if your tree is a star, you can compute Chamberlain Current winners in FPT. Okay, so let me actually explain the intuition behind that. So it's important here that I'm using the border scoring function for my Chamberlain Current rule. So remember, what does it mean to have preference single peaked on a star? Right? You have this one really good guy, one who is ranked by everyone first to second, right? And other candidates are ranked arbitrarily. Okay, so if you're choosing Chamberlain Current committee, well, seems like your best bet is to take that one really good guy at the center of your star. Right? It's not necessarily the case. So it may be that he's ranked second by everyone, and you can form your committee from top ranked guy. So you should be checking for that first. Right? So what happens if you just take guys who are top ranked by some voter, right? And if there's at most k of them, you already have a winning committee. You don't need to take that center guy. But if that's not working for you, you should take that center of the star. That will satisfy some voters completely, and to some voters it will give them second most preferred candidate. Right? So once you've taken that guy, you still have k-1 slot, and you have your bunch of voters who are not satisfied perfectly. Right? So then you can try to greedily add candidates to shift those voters from being kind of almost perfectly satisfied to perfectly satisfied. Right? So each candidate will buy you some number of such voters so you can choose greedily. Right? And extending that idea, okay, to graphs that are almost stars, so have a small number of internal leaves, so it's actually a very similar argument. Right? Okay, so that actually works. It doesn't work for other scoring functions if you're not working with border scoring function. Right? So for other scoring function, you can get hardnesses out for stars, but for border it works. But interestingly, you get hardness for general trees. Right? So if your tree is ugly, so it doesn't have a small number of internal vertices, it doesn't have a small number of leaves. If it's, for instance, if it's sort of a balanced binary tree, then Chamberlain Current is actually hard to compute. Right? So you need a tree, but not just any tree, so you need a nice tree. And this is one reason why we're interested in constructing nice trees. One reason why we want an algorithm for constructing a tree with a small number of leaves in that paper, and we could have it. So that's the reason why we wanted to construct trees with other nice properties, such as small number of internal vertices in this paper, and we can have it. Right? So these two algorithms for recognizing structured preference and exploiting structured preferences come nicely together here. Right? So it can't be just any tree, you need a specific tree, and you actually need to find that tree. And once you have that tree and it's nice, you can run kind of these algorithms. Okay. So that's that story, and I think this is all I had to say, so let me stop here.